Let's look at an example of how to use the ideal gas law now. Before we do, let's look at a couple of useful facts and definitions for the ideal gas law. Very often you'll see problems that say you are at standard temperature and pressure. Well, what does that mean? Well, standard temperature would be our base temperature, which we often take to be the freezing point of water, 273 Kelvin or 0 degrees Celsius. And standard pressure would be the average pressure at sea level of the atmosphere. And so we call that 1 atmosphere of pressure, which is equal to 101,325 pascals, which is indicated here with the 1.013 times 10 to the fifth. If you convert that into kilopascals, that's 101.3 kilopascals. Okay, now the volume of 1 mole of an ideal gas, another helpful bit of information, any gas, any ideal gas, whatever it is, 1 mole of that gas would have a volume of 22.4 liters. Now, let's ask ourselves, what happens if we change the state of a gas? Well, first of all, let's assume that the amount of the gas, in other words, its mass, does not change. Well, the equation of state at both times, before the change and after the change, is still going to be the same. Pressure times volume is equal to nRT. So we use the same equation for both states. Now, we're using the fact that mass is a constant. So we divide both sides by temperature, then the right side of the equation is a constant. In fact, it's the same constant for both states. So if we set them equal to each other, then we find that pressure times volume divided by temperature is a constant number. So whatever your pressure and volume and temperature are, their combination, as you see here in the equation, should not change. A couple of important points to make. Whenever you use the ideal gas law, the temperature always needs to be expressed in kelvins. It has to be in kelvins. Also, the pressure must be the absolute pressure. You can't take a pressure gauge to the tire in your car and use that pressure in the ideal gas law. That won't work because there's also atmospheric pressure inside of your tire that balances and cancels out with the atmospheric pressure on the outside of the tire. If you have any questions about gauge versus absolute pressure, Chapter 10 in your textbook does a really good job talking about that. I also need to point out that when you use the ideal gas law, here in this, when you use this relationship here, the exact unit for pressure won't matter as much, which we'll see in a couple slides. But when we do the ideal gas law up here, pressure and volume do matter what units you use, because they have to agree with the units of your constant R. Okay, let's use this equation, this relationship of PV over T. Let's say that you have 1.6 moles of an ideal gas at standard temperature and pressure. What will be its temperature if you increase the gas to 2.5 atmospheres and decrease its volume to 2/3 its original volume? Okay, so to start off with, you know that you have 1.6 moles. And you know that your starting temperature and pressure are 0 degrees Celsius, but we have to use Kelvin. So that's 273 Kelvin. And your pressure to start off with is 1 atmosphere. We'll go ahead and just leave it at 1 atmosphere for now. Let's make it 1.00 atmospheres though. Okay, now the last thing that we need to ask, what is our initial volume? Well, you were told in just a couple slides ago the volume of 1 mole of an ideal gas. So if 22.4 liters is equal to 1 mole, then what volume is equal to 1.6 moles? I'm just using a simple relationship here. Sorry, a proportionality equation. If I solve for volume, that's going to be 1.6 times, well, let me see if I can write that properly. 1.6 times 22.4 liters, and that will give me 1.6 times 22.4 gives me an initial volume, these are all volume 1, of 35.84 liters. Okay, so we have our initial volume, but that's not what we want. We want to know what will be its temperature if you increase the pressure and decrease the volume. Well, to do that, we use our ideal gas relationship here. So let me change my ink color here. There we go. So we know that P1 V1 over T1 is equal to P2 V2 over T2. If we solve for the temperature, T2, then that's going to equal P2 V2 times T1 over P1 V1. Just using algebra, that's what we get. So the temperature then is going to equal P2, which is 2.50 atmospheres, times V2, which is going to be 2/3 of its original volume, which was 35.84 liters, times its initial temperature, 273 Kelvin, again, you have to use Kelvin, divided by your initial pressure of 1 atmosphere, times your initial volume of 35.84 liters. Now notice here that the volume cancels. Everything on top is multiplied, so it won't matter what the initial volume was. In fact, the number of moles you have is completely irrelevant as well. All that matters is that the final volume was 2/3 of your initial volume. So that's for this case because I'm dealing with 2/3 of its original volume. If I were given an actual final volume, like a volume of 30 liters, yeah, you're right, they would not cancel out because they're completely different numbers. But since we're dealing with 2/3 of our initial volume, it cancels out. All right, finish solving this. So, plugging this into my calculator, 2/5 times 2/3 times 273 divided by 1 would be 455 Kelvin. I'm just double checking that, making sure I got that right. Times 273. 455. Now, here's an important point. The units need to cancel on both sides, but when using this relationship equation, the units themselves don't really matter. In the last equation, in the last slide, excuse me, we used pressure in atmospheres. What happens if we use them in pascals instead? And just for reference, I wrote them down already for you. So T2 we decided was equal to P2 V2 T1 divided by P1 V1. So that would be P2, 2.5 atmospheres, would be 253,313 pascals, times 2/3 of my initial volume, times the initial temperature, which is 273 Kelvin, divided by P1, which is 101,325 pascals, times whatever V1 is, which, again, your volumes cancel. Now, if I plug this into my calculator, why don't you guys go ahead and plug this into your calculator. Go ahead and pause the video right now, and I will tell you what it is. If you did this calculation, you should have come out with 455.0 Kelvin, exactly the same as we got on our last slide. So as long as the units cancel, it does not matter what the unit is. If the units don't cancel out, then yes, you'd better pay attention to the units, especially if you're dealing with like the constant R. Make sure your pressure and your volume are in units that agree with the value of R that you use.